So let's start. We're going to do section 1.6, logarithms.
That's an air raid.
Logarithms. Oh my god. No, not logarithms. It's like lightning strikes and all sorts of things happen. How many of you are familiar with logarithms? Like, are they that scary? How many of you have seen logarithms before? Okay, so maybe a third of you or so. In my other class today, like most of the people seem to have seen logarithms, but it's okay. We're going to start again, as always, from the basics. So we're going to build it from the ground up, and so all of you will be as good as logarithms now. Okay, so let's start with the definition. What is a logarithm? The logarithm a number to a given base is the power to which the base must be raised to give the number. Here's sort of the notation of how this will make sense to you. It's written like log. The base is the little number that comes down here. It's like the base. The number is here. So we're taking the logarithm of a number, kind of like f of x. The log is a function that does a certain rule. And what the output is the power that you need to raise the base to in order to get this number. Right? So, i.e. This is rule 1. This defines the logarithm. So I'm going to take this sentence and I'm going to write it in math symbols using this notation. This says log to the base a of b equals c is exactly the same as saying if I take a raised to the c, I will get b. The logarithm of a number to a given base is the power I need to raise the base to in order to get that number. So I need to raise the base a to the power c in order to get the number b. That's how we want to think of logarithms. So for example, if I ask you what is log to the base 2 of 8? 3. It's 3. Why? I need to raise base 2 to the power 3 in order to get 8. So that's what a logarithm is. And now you're like, what was wrong with 2 cubed equals 8? Why this complication of this entire new function? It turns out that this function actually makes a lot of things a lot easier. Because it takes the logarithm, its output is the power. And you might notice from a bunch of rules that usually when you're applying rules with exponents involved in them, the operation that's going on in the power is always easier than the operation that's actually going on with the entire function. If you look at multiplication of two things, right? Like multiplication, right? If you only focus on the power, what's happening? Addition is happening, right? You can talk about the division, right? Which has all sorts of, it's rife with all sorts of terror, right? Because you have to worry, do I divide by 0, blah, blah, blah. But what's happening in the power? Subtraction. Not that big a deal. I can take exponentiation. I can raise something, I can take something to a power, raise it to another power. What happens in the power? Multiplication, right? So in the base, overall, we can be doing very complicated things, but if we simplify it to the power, it actually becomes not so complicated. It also ends up helping us to break things down. So in some of your science classes, you might sometimes be asked to plot one variable versus the log of the other variable, because it really breaks things down into simpler terms. And so if your one variable is just huge compared to the other one, you might figure out what the log looks like. And I think there's a window that's half open that we need to fix.
I think it's the universe telling us we shouldn't do math right now.
No, we have to fight against the universe.
Isn't that our entire
exactly. Exactly.
So,
What makes us human beings is that we fight against the elements and we conquer the elements. Right? We don't just accept it and give up. Okay, so where are we? Okay, let's talk about some other rules in the same vein of this. We're going to kind of, this is where our intuition is going to lie. So let's talk about rule 2. Rule 2, I'm going to kind of do this, guys. This tells us that the logarithm to a base of something to a power, we can turn that into a multiplication. So for example, I can say log to the base 3 of x, or log to the base 4 of x cubed. I can write that as 3 log to the base 4 of x. I can turn powers into products in this way. Rule 3, I can turn multiplication into addition. Alright, so this is xy equals log to the base a of x plus log to the base a of y. Right, so if I'm taking a log of something that's being multiplied, I can actually break this up into an addition of logs. Right? When you're multiplying the bases, you're adding the powers. And then, so an example here would be something like, let's say I have log to the base 3 of 2x squared. I could write that, realize that this is 2 times x squared. I can write that as log to the base 3 of 2 plus log to the base 3 of x squared. And I could even apply this rule and make it that even simpler. I can take this 2 and bring it down in front. Log to the base 3 of 2 plus 2 log to the base 3 of x. Right? So relatively speaking, I'm working with 2x squared. It's a very complicated function. Well, it's complicated if you're related to just the function 2 or just the function x. Right? 2x squared would be more complicated than dealing with 2 and x. Okay, that's kind of the idea behind the logarithms. The point is actually to simplify certain computations. So don't let the howling wind fool you. Logarithms are very useful, and logarithms saves lives. Like literally, like the guy who invented a logarithm was the whole way a logarithm came up was in nautical navigation, right? The calculations to know when you send out a ship out to sea around on an almost spherical planet, navigation becomes very difficult. And so a lot of people got lost at sea because they couldn't calculate their bearings correctly. And developing the logarithm helped to do that a lot more efficiently. You could do a lot more complicated calculations in a relatively easy manner, and it literally saved lives. So the invention of this was by a guy named Napier, and you can read up on the history if you want, but I won't go into that. So yes, it greatly simplifies a lot of complicated calculations. So once you can get over the ugly notation, once you get used to it, it's not going to look that ugly to you. You would realize it really does make your life easier. Let's do the one with division. This says that log to the base a of x divided by y. Division, it can change into subtraction. And it turns out the log of a number is always smaller than the number itself. Okay? So you can go from dividing 2 huge numbers to really subtracting 2 smaller numbers. Right? That's the power of a logarithm. Okay? So example, I can say log to the base 9 of 2 over x squared is really log to the base 9 of 2 minus log to the base 9 of x squared. And I can take log to the base 9 of 2 minus 2 log to the base 9 of x. Dealing with 2 over x squared might be difficult, but dealing with 2 is not, dealing with x is not in certain contexts. So these are the first 4 rules. They're very important that you know them. You should memorize these first 4 rules and know them very well. The remainder of these rules I'm going to give you is, they make your life a lot more convenient if you happen to memorize them, but you could actually derive them. from what I've already written here. Well, the fifth one is also kind of difficult to derive, so you probably should memorize that as well. But the others are going to kind of just fall into place once we really understand the first four rules. Rule 5, this is called, it has a name, it's called the change of base formula. There's a rule that says we can change the base of a logarithm to a base that's more convenient. So for example, if we have log to the base a of b, this is actually equal to log to the base c of b divided by log to the base c of b. And c is some base that you can introduce that's more convenient to work with. Sometimes you're given a problem and it's set up in one base, but you want to convert it to another base because it's easier to work with. So I'll give you a simple example here. What is log to the base 4 of 8? Yeah?
Log base, it equals log base 10 of 8 over log.
Yeah, well, that's not convenient. Like, you can actually work this out in your head and get an exact number without needing a calculator. So the question that is being asked here is, what power do I have to raise 4 to in order to get 8? Right? And you can start to think about it. You're like, okay, if I raise 4 to the first power, I get 4. Okay, that's smaller than 8. Go bigger. 4 to the second power, well, that's 16. That's already bigger than 8. So it's definitely a number between 1 and 2 that will give me 8. But which number? It's hard to really know for sure. Do I just go directly in the middle? You can't actually know for sure unless you just realize no one thinks of base 8 in terms of base 4. There's a more convenient base for these two numbers. What do you think it is? 2. I know about 4 in base 2. I also know about 8 in base 2. So let's go from base 4 to base 2. By this rule, that's base 2 of 8 over log to the base 2 of 4. Now each of these individually I know. Log to the base 2 of 8 is 3. I have to raise 2 to the power of 3 to get 8. Log to the base 2 of 4 is 2. I have to raise 2 to the power of 2 to get 4. So 3 over 2 is the answer. And that's actually easy to check. You take 4 to the 3 over 2, that's really just the square root of 4 cubed. That's 8. Yeah.
You can use absolutely any base.
Any base that's convenient, yeah.
So like natural log.
Yes. We haven't gotten there yet, but yes. You want to use a base that's convenient, which, yes, sort of suggesting to what you were talking about. We said what, for y equals a to the x, a is the base. And in calc, y equals, what base was the most convenient? We discussed that last time. Base e. So sometimes you might be given a problem in some random base, but you're going to want to convert it to base e because it's easier to do calculus with base e. And if you can rewrite the exponential in terms of a logarithm, you can change the base with this formula, and that will help you to do calculus on it. In fact, I am going to use this to derive some formulas in calculus when we have weird bases and we want to use base e. In this case, though, base 2 was the most convenient if you don't want to have to use a calculator. That's called the change of base formula. These are some other rules that knowing them will quickly help you simplify a lot of problems, make your life a lot easier. They don't really need to be called rules. You can put rules in quotations if you want. But rule 6 is just some quick facts that you can be aware of. What is log to the base a of 1?
0.
0. Why is log of 1 0? Because I take a raised to the power of 0, I get 1. Take any non-zero base raised to the power of 0, you'll get 1. Right? So you can just know that. Based on the definition of a log, this follows right away. Let's go serve the other. What is log to the base a of 0? Right, so let's say my base is 2. What power do I raise 2 to in order to get 0? There is no number you can raise 2 to in order to get 0. This is undefined. In fact, you'll realize, for our definition, log to the base a of x is undefined if x is actually negative, less than or equal to 0. Because we assume here that our a is a positive number that's greater than 1. Why? Because if a is a positive number that's bigger than 1, that's less than 1, I can think of it as 1 over a number that's bigger than 1 and use the base rules in the denominator. If a is negative, I can just like factor it off and work on it separately. So really the theory, it's a lot nicer and it works out a lot more fluid if we just assume it's a number that's greater than 1. And all the other special cases we'll do as they come. But in this class, we'll never actually be taking logs of anything that's less than 1 anyway. And of course, equal to 1 is just redundant. Like if the base is 1, 1 to anything is just always 1. You'd only ever have one number to deal with there. So this is always the assumption. So you're always thinking of the base as a positive number. There is no power you can raise a positive number to in order to get 0. So you can automatically know that log of 1, regardless of the base, is 0. And log of 0 is undefined. In fact, log of anything negative is undefined. That is going to be a fact that's going to be reinforced with something else I'm going to tell you. But for now, let's move on to a couple more rules. Rule 8. This might seem silly, but it's nice to know it because it helps us solve equations pretty easily. This says log to the base a of a to the x is equal to. What power do I have to raise a to in order to get a to the x? X. So that was nice. Okay. Rule 9. This one kind of goes the opposite way. If you take a and you plug a log in the power, what does that give you? That also gives you x. That one's a little bit tougher to prove. It's not difficult. It's just like 2 or 3 steps, but I'm not going to prove it here. I proved it in my 1207 class, but that's Calc 2, so they can worry about that. I don't want you guys to actually worry about the proofs of these rules, just know the rules. Some more information on notation. We said that E is a convenient base, and to that effect, we do want to somehow denote when we're working in base E in such a way that it stands out. And we will do that by this symbol, ln. ln of x is a log. Whenever you see it, you will assume it means the base is E. Right? I'll never actually write this down, log to the base E. Whenever that's what is meant, this is what I will write. This is called, and now I remember I forgot to tell my last class what the name was. This is called the natural logarithm. Just like how e to the x was the natural exponential, this is the natural logarithm. So when I write ln of x, know that it is log to the base e. That means I'm thinking of e as the base when I'm doing my calculations. Another notation, if you just have log x, that means log to the base 10. So if I just write log and I don't specify the base, it means there's a base 10. Right? If I write ln of x, it means that there's a base e there. In all other situations, I will specify the base. I will literally write the base down. Another thing someone had a question about. The notation, the x is higher than the a just by how you use the position of things, but it doesn't mean there's a division or anything going on here. This is more like a label to identify what base. It's kind of like when you have a radical of x and you write a little number here. right? It doesn't mean like you're actually multiplying or dividing or doing anything. That's just saying what root you want to take. In the same way, this little number down here, it's written very small, and it's just identifying to you what base you're working with. It doesn't actually, there's no like algebraic manipulation between these two things, even though they're right beside each other. I just want to make sure you know that. So if this was something like log to the base 2, and up here this was 18, you couldn't actually cancel this at 9, and you can't do things like that. I just wanted to make sure you know that. It's a notational thing, this little number down. Okay. So these are notations. Okay. So this is our standard logarithm. These two guys are the functions that will be on your scientific calculator, right? So if you just have log, it's base 10. You have ln, it's base e, and those will be on your calculator. If you need to work in any other base on your calculator, use the change of base formula. So on your calculator, if you wanted, if I ask you to compute, I won't, but in case I ask you to compute, log to the base 7 of 13, what is that? Write it as a decimal. What you would do is you can put in log 13 and divide that by log 7, and that will give you a decimal, right? You can use the change of base formula. But I won't actually require that. I mean, log to the base 7 of 13 I would accept as an answer. Okay, so that's just some notations about bases. In higher mathematics, this would take over that, so in case of you guys jump on the math major train later on, and you're reading some advanced math books, and when you see this, it actually means ln. If you're going to like higher computer science, this would always be base 2 because they usually work in binary. But at this level, we all work in base 10. We have 10 rulers that we count on, so that's the standard right now. Here's something else important. So if I think of these two guys as functions, and I take these two rules together, what are they actually telling me?
They're inverted.
They're inverse functions. Remember, there's a rule that says like, oh, if you have a function f of g of x, and when you plug one into the other, you get x, and then if you do it the other way, you also get x. That is one way to define what's an inverse function. And knowing that logs and exponentials are inverses of each other can actually give us a lot of nice properties. It will actually tell us a lot of algebraic properties about a log, as well as how to draw their graphs pretty easily by knowing that they're the inverse of an exponential, right? They kind of cancel each other. You can think of a log, if an exponential takes x and does something with it, the log is going to cancel that effect and give you back the original thing. You can also think of, if you have an exponential, a log is doing something, the exponential can cancel it and give you back the original thing. When you plug one function into the other one, they undo each other. One function reverses the other with these two guys. So they are inverse functions. And that actually can tell us a lot. This means, one, we can use logs to get rid of exponentials. And vice versa. So if you have an exponential in your equation and you want to get rid of that exponential in your equation, you can use a log to kill the exponential and rewrite it in a different form. And if you have a log in your equation and you want to get rid of the logarithm in your equation for some reason, you can use an exponential to kill that log. That's one thing that it means. It also means that the graph of y equals log to the base a of x is obtained by, how do you get the graph of an inverse function if you know the graph of a function? You guys remember? Do you remember?
think so. Can you just put your output put it on over, like 1 over your value?
No, that's the reciprocal. It's not exactly the same as the inverse. If you're talking about actually finding a formula, what you do is you switch the x and the y and you solve for y. That's how you find the inverse function, remember? But I'm specifying graphs here. How do I get to a picture? If I give you the picture of a function, I tell you, oh, it has an inverse. How would you find the picture before the inverse? It's a reflection operation. You're reflecting y equals a to the x in the line. Which line do you reflect? Do you remember?
Y equals X.
Y equals x, because you're switching the input and the output. So you want all your y values to become your x values, all the x values to become your y values. That tells you that because you know the graph of the exponential, y equals a to the x, you can take that line, y equals x, and you can mirror it over that line. You will get another graph that looks like that. And that graph is your log graph. What does it pass through here?
0, 1.
Well, 1 comma 0, right? So it passes through 1. Why? Because this one passes through 1 over here. Also, we know that the log of 1 is 0. So that's why it will cross the x-axis at 1. So by knowing it's an inverse function, we can easily figure out its graph. This shows the following. So if I want to have y equals log to the base a of x, where my a is greater than 1, the graph would look like this. Which again you can see log of 0 is not defined, but also log of anything negative is not defined. The log only exists on the right side of the y-axis. But the thing is, log is just a function like any other function. It behaves the same way under transformations as any other function does. So if I put y log of minus x, what does it do when I replace all x with minus x? What would that graph look like? Placing all x's with minus x's do what? Yeah?
Does it flip over the y-axis?
Flips over the y-axis. So the graph of that would look like this. What about minus log to the base a of x? When you put a minus in front of something, what does that do? Yeah?
Does it flip it over the x-axis?
So it takes this graph and it flips it over the x-axis. So it's going to take this and flip it in the x-axis. So it will look like that. What if I make both inside the x, the inside negative, and the outside negative? Well then that's just going to flip this one. That would look like this. Right, so logs are functions. They will respond to transformations just like any other function. So I just want you to be aware of that. You can manipulate them, you can shift them, you can stretch them, you can do all sorts of stuff. And algebraically, it follows the same rules. So this is just like any other function. Under transformations. Sometimes I have to emphasize these because sometimes you write something that students aren't familiar with the notation and it looks scary or weird. They just think that, oh, the rules don't apply. No, the rules still apply. You can just, oh, math doesn't work anymore with this thing. And they start randomly dividing stuff, randomly multiplying stuff because they don't know what to do. The log is just like any other function under transformations. And in that way, also, very important, ln of x is just another log. Meaning, all the log rules I mentioned before, they still apply to ln. Right, so for example, if you see ln of something times something, you can break that up into an addition. Right? If you see ln of e to the x, that's just x. If you see e to the ln of x, that's just x. Right? That's rules 8 and 9. Right? This was rule 2, or whatever order I put it in. Right? If you see something like ln of e, what's that? 1, right? Because that's e to the 1. So I'm just applying this one. What if you see ln of 1? 0. Because log of 1 is always 0. Right? So you might see this symbol, all the log rules apply. Everything that was a log rule applies with this guy. It's just that the base is e, but all the rules still apply. So don't think you have to do something different when you're working with ln than when you're working with some other logarithm. It has the same rules, it has the same graph. The graph of ln also looks like this and passes through 1. Right? It's just the steepness. The base will change the steepness of this graph, but they'll all behave the same way. So that's something also important for you. So don't get scared by how things look. These guys are functions. If you do a transformation, you take a negative, it flips in the x-axis like any other function. Okay? Don't be racist. Let's do some examples. You're like, it's a logarithm, it's not as good as a polynomial. Everyone is the same. Down inside. Okay, let's do some examples. I want you to simplify the problem. So a e to the 5 ln 2. E. 2 to the log 2 is 2 of 2 to the 5. Log to the base 2 of x minus log to the base 2 of x squared plus log to the base 2 of x to the 4th. I want you to expand this. E to the ln of x squared minus 5 ln of y. E. Well, not expand. I want you to combine this. That's already expanded. This one I want you to expand. Expand. To the most simplest ways possible. 2, I want you to actually solve for x. First example, there is going to be ln of x equals 7. E to the 2x minus 7 equals 10. C. 3 equals 5, e to the 3x. D. 2 to the x squared plus 1 equals 5. When we complete these examples, we'll complete the section. Okay, how do we simplify that? Okay, go. E to the 5 ln 2. Simplify. Yeah.
Would it just be 10 because each ln is 1, so the 5 is 2?
So this would cancel, and that becomes 10.
Yes.
Incorrect. Why? It's important you know why. It's a very common mistake. Yeah?
Well, if you multiply by a log, doesn't it raise the, well, wouldn't the 2 be raised to the 5th power? So it'd be 32.
Right.
Because and the e to the ln would cancel out, so you get 2
Yeah.
to the 5th.
Okay. So this is the important point here. When you're given a rule, when you apply that rule, it has to. When you're trying to apply that rule in the real world, it has to look exactly. The rule is your template. It has to look exactly like the rule in order to be applied. So you have this rule, and that's the rule that you want to apply, right? Or you could even think of it as this rule. So I get that that's the rule you want to apply. You want it to be like, oh, let's cancel these two and get that back. But why couldn't I apply that rule here? What was off? What's something very different about those that was here? The 5 that's in front. Notice that in the rule, there is no number that's in front here. Okay? So when you're applying the rules, you have to be very careful. It has to look exactly like the rule to be able to apply that rule. The fact that there was a 5 in front of the ln, you can't have a number in between the e and the ln. It's not going to work to cancel it. Right? There's a number in between here, it can't work. The e and the ln, or the a and the log, they have to be right beside each other. Right? There's something in the middle, you have to get rid of that thing. Right? Because that rule won't apply yet. So there are a couple ways you can do this. So I can say, for one, I can use the rule that says something in front of a log multiplying, I can move it up as a power. Right? So that was like rule 2 or something. Okay? And now it looks exactly like that. I have e, and in the power, there's an ln right away, nothing in front of it, no powers or anything weird. It's just e to the ln of something. E to the ln of something. And so now I can think of those as canceling because they're right beside each other. You can effectively think that, like I said, you don't think of it as being a division here or anything, but you think of them as undoing each other once one is plugged into the other. And so you end up with 2 to the 5th equals 32. Right, but be careful of how you're applying these rules. There was another way you could simplify this by first applying a law of exponents. For one, we know how powers work when they're being multiplied. Here I have a 5 times an ln 2, right? When you have a power being multiplied, what does that mean? What was the rule here? What expression gave me something like that? Yeah?
X to the a plus x to the b.
X to the a plus x to the b? No, that's not a rule. Yeah?
X to the a to the power b.
X to the a raised to the b is what gave you that guy. So remember your exponential rules, remember all the rules. So in fact, when there's a power, where there's a multiplication in the power, I can literally like factor one of those powers out. So one thing I could have done here is when I had e to the 5 ln of 2, I could like factor out that 5th power. That's just me applying this rule. And now inside the parentheses, the e cancels the ln rule would take effect because it's right beside each other. And so that would give me 2 in here. And again, I get 32. The moral of the story is the rules are your templates. It has to fit exactly on top of one of these rules in order to apply them. Anything that's off, you need to somehow use algebra to manipulate it, right? Why your algebra is going to be important, why remembering all these rules are important. So when I was doing this, it was Oh yeah, everyone knows this, but yes, you're going to be applying that in a context where it looks weird. You still have to know the basics in order to change things. So that actually simplifies to 32, e to the 5 ln 2. What about the second one? 2 to the log to the base 2 of 2 to the 5.
It's also probably 2.
How do you know?
Because the log base 2 is 2, they cancel each other out, and it's just
Yeah.
base.
So how does it cancel that chart out? Because the base is a 2, the log has base 2, so they cancel each other because they're right beside each other. There's nothing in between them or anything like that. So then you're just left with 2 to the 5th, which is again 32. You could also have done that in the power instead, by the way. Right, so when you have that, you can think of these two canceling. It would still apply because here's the base of a log and the base of an exponential. So that one was applying like rule 8, this is applying rule 9. You'd still end up with 2 to the 5 because the 5 would be left over here and you get 32. So there's often many ways you can do it, just make sure when you're doing it, you're applying whatever rule you're using in the correct way. See. Combine the logs. What do we do?
Log base 2, and then in parentheses, x divided by x squared.
Okay, so here's a subtraction of logs. We have a rule for that. It means there's a division of these two things. Okay.
Log base 2, and then in parentheses, it's going to be x over x squared times x squared.
Alright, so again, this is another log rules. I'm adding two logs of the same base. It means I can multiply the two things and take the log on the outside. So this would simplify into log to the base 2 of x cubed. Or I can write that as 3 log to the base 2 of x. Here's a common mistake. So don't do this. So it's quite often that a student might see this and they would do something like the following. They would think that this is log to the base 2 of x minus x squared plus x to the 4th. And why would that be wrong?
Because you're not simply subtracting the x and the x squared. When you separate a log like that, you have to divide
Yeah.
it.
So one rule is a lot of you guys are, of course, everyone is supposed to be used to the distributive law here. Logs don't distribute. Right? Again, remember, logs are kind of the reverse of exponents. Exponents don't distribute, right? So don't think a log is going to distribute. As well as, there is no rule. There was no rule that says if there's a plus on the inside. You'll notice that I never had a rule that gave you this kind of quantity and say this. Log plus log b is not a rule. Right? So don't do it because you feel like it, or because it makes sense, or because it reminds you of some fondly of the distributive law. It does not matter. There is no rule that says you can do that. Don't do it. The rule says when things are multiplying here, it becomes a plus out there. So don't think that becoming a plus in here becomes a plus out there. That's not the rule. It's a very common mistake. And a couple students in my other class suggested doing that. That's why I wanted to bring it up with you guys. Just in case anyone was thinking of doing that, that would be the incorrect thing to do. This would be wrong. Right? The correct way is to follow the rules. Subtraction means division inside the log. Addition means multiplication inside the log. And then we can do that. There was another way, again, multiple ways to do a lot of these problems, but just make sure you're applying the correct rules in the correct ways. We could have done, can anyone think of another way to do this? Did someone see another way when they were thinking of it?
Do the addition first.
Sure, but it would be very similar. You'd still do multiplication. There's something using another rule completely. Yeah?
Did you do, instead of doing the subtraction first, you do the addition first?
You could, but that's what she said.
Sorry.
That's what she said.
How old are you?
Correct myself. Yeah. There's a rule that had to do with powers, right?
Or you can bring a.
We could actually bring those powers down. That was another option. We could have done this. Bring the 2 down in front here. Bring the 4 down in front here. And now this is like 1 apple minus 2 apples plus 4 apples. You could just combine them. And that would give you 3 log 2 of x, which is exactly what we ended up with. So it was another strategy, but I'm applying a totally different rule here. Here I'm applying the rule for subtraction and additions of logs. Here I'm applying the rule for log bringing powers down. But I'm applying the rule in the correct way. All right, so there'll be multiple ways you can do a lot of these problems. Just make sure you're applying the right rule at the right time, in the right way. It's very important that you're extremely OCD with these sort of things. And if there's a rule that doesn't look like the thing you're doing, don't do it. No matter how it feels, if it feels right in your heart, it doesn't matter. Just, it's like if a rule, there's no rule that says I can do this, just don't do it. Which means, first of all, you need to know all the rules. You need to have them memorized and know them very well, so that you can know when something fits the bill from when it doesn't. Let's look at another one. Simplify. E to the ln of x squared minus 5 ln of 12. I think that was D or something. Yeah?
So it's gonna be E ln x squared minus ln y to the fifth.
Okay, so you apply that rule where you can take this and bring it up as a power.
And then you can rewrite that again as e to the power of ln in parentheses x squared divided by y to the fifth. And
Okay,
then,
now we applied the rules where subtraction of logs is just a log of the division.
and then e to the ln cancels out. And you
E and ln are right beside each other, and the ln is in the power. You can think of them as canceling out. And we end up with x to the y over 5. There are other ways to do it. There's so many ways. Like I could have thought of this as e to the ln of x squared divided by e to the ln of y to the fifth, because I'm using the exponential rule that when you subtract powers, it's actually a division. And then these guys would cancel right away, and again I would get to here. Again, multiple rules. Here I'm applying the laws of exponents to simplify first. Here she applied the laws of logs in the power to simplify first. But they're both valid laws, and we're applying them correctly. You would get to the same thing. Neither way is preferred. It's all personal preference. Whatever you see first, you just do that. Just make sure you are applying the rule correctly. So that simplifies to x squared over y to the fifth. Right? And we don't have to worry about division by 0 here, because 0 doesn't even work in the log in the first place. Right? So the y wouldn't be 0. So the request here was to expand this one and simplify it. So here we were contracting a log. We took a bunch of logs and combined it into one big log. I want to literally do the opposite here. I have one log separated into a bunch of other little logs. What can we do here? Yeah?
Can you do half times the natural log of x squared minus 1 minus 2 natural log of x times x plus 1?
You're skipping a lot of steps here. I'm going to go back and fill in some steps, but this is what you said here.
Yeah.
That's incorrect. It's because you're skipping steps. Don't just try to do too much at once. Well, let's see why this is incorrect. Let's break it down. Simpler steps, one rule at a time. What would you do first? Yeah?
You could make it so it's ln radical x squared minus 1 minus ln x minus x plus 1 squared.
Right, that's a division turned into a subtraction. Now the mistake from doing this in your head is you'd think, oh, this 2 can just come down here. But why can't you do that?
Because there's an x there.
Because there's an x here. In the rule, there's nothing in front of the thing that's raised to the power. Here's the thing that's raised to the power. There's something in front of it. You cannot apply that rule. You don't have the right scenario. There's nothing in front of the guy with the power in this rule. Right? So you can actually bring that 2 down. Doing that would be premature. It's not going to work. Okay. What else could we do? Yeah?
Well, since our square root of x squared plus 1 is basically raising it to the 1/2, you can bring 1/2 to the outside.
Right, square is just a half power, so I can simplify that as bringing the half down to the outside. Sure.
And also we can factor, sorry.
Well, let's move to this one.
You can do ln of x plus ln of x plus 1 squared.
Is that
That'd
okay?
be minus ln of x plus
Be
1.
minus y.
Because that log is
Parentheses. Every time you're subtracting it, everything's happening in parentheses, so that negative sign would distribute, and that would be minus. If you don't write the parentheses. If you want to put a plus here, you have to put those parentheses in. Okay. And so this guy, pretty simple. This guy I'd probably simplify to just bring that. Now I can bring the 2 down. There's nothing in the way. It fits exactly to the rule. So we have that. Yes, and we can go further. So now
Yeah, we can factor x squared minus 1.
x squared minus 1 is the difference of squares. We know how to factor that. That's x minus 1 times x plus 1. And now what? Yeah, so now what?
The product rule. So ln of x minus 1 plus ln of x plus 1.
Yes. And again, it's in parentheses. So this half here is
Times
going to have
that
to
whole
distribute. So you have to remember your parentheses. It's going to be x minus 1 plus a half ln of x plus 1. Because this is happening in parentheses here, when you split this up, the half has to apply to both the logs separately. And so we'll end up with this. Minus ln x minus 2 ln of x plus 1. Notice that these two guys are the same. It's an ln of x plus 1 and an ln of x plus 1. I can just combine them, right? Half an apple minus 2 apples. So it's 1 over 2 minus 2 over 2 minus 4 over 2 is actually minus 3 over 2. And this guy, that's a half ln of x minus 1 minus ln of x. And that's pretty simple. Can't really break any. There are no more log rules to apply here. log of something plus something, I don't have a rule to do that. Nor do I have a rule for log of something minus something. So that's as far as I can go. So both of these two kinds of things, these are necessary skills. You need to be able to, given a bunch of logs, combine them into one log, and given one log, separate it into a bunch of logs. Going from many logs to one log is very useful in solving equations. Going from one big log to many little logs is very useful in actually doing calculus. So if we want to do a calculus on a log function, this is a much better scenario than this. But if we want to solve an equation, then this would be the better scenario than that. And we'll see why. When we actually get to, when we start doing calculus and we start doing ln and start doing calculus with ln, you'll see why dealing with this is going to be a lot easier than dealing with that. So let's get to the solving equations part. ln x equals 7. Solved. How do you solve this for x? Yeah?
Raise take each side and put it so like e to the ln of x.
Right, you can put that side inside of e and this side inside e. It's an equation, so we have whatever we do to one side, we have to do to the other. And so in this first scenario, that would cancel. And so that would just right away give us x, and then this would give us e to the 7. Right, so this is what I mean. You can use an exponential to get rid of a logarithm. I needed to get the x, but it was stuck inside of a log. Use an exponential to get it out. You can kill the log by using an exponential. It's also worth noting that this actually applies directly from rule 1, right? When the base here is e, this raised to that power should give us this number. So you could actually also think of it as applying rule 1. It's much more common for students to do this though. Just, if you see an ln, you want to get rid of it, raise both sides to the base to get rid of that ln. What about this one? Right, this is the opposite. Here I have an exponential that I want to get rid of. What I can do is I can ln both sides. I can write this in place. In this case, the ln is right beside the e. They would cancel each other. This would give us 2x minus 7. And this side would give us ln of 10. And then from here it's just algebra, so this is 2x is equal to ln of 10 plus 7. And this means that x is equal to ln of 10 plus 7 all over 2. Do not add the 10 and the 7, right? Because the 10 is inside a logarithm. It's not out in the open. Okay, so you can't actually move things inside of the ln. This guy is stuck inside of an ln. The 7 is being added separately. So yeah, so normally you want to solve a log equation, you can use exponentials to simplify things. If you want to solve an exponential equation, you can use logs to simplify things, because exponentials and logs, they kill each other. They are inverse functions. One undoes the other one. So that gives us a nice way of solving equations. Okay, let's do this one. 3 equals 5e to the x to the 3x. Okay, what do we do here? We would first divide by 5. Why didn't you just ln both sides right away? There's an e.
Because then you're stuck with 5.
Because if you put ln, there's a 5 between the ln and the e. Things aren't going to cancel. It would not fit the rule. So there was a 5 in front of the e. You first have to get rid of that 5. Now we can ln both sides. ln is right beside the e, cancels. That gives us 3x. This side we have ln of 3 over 5. And so my x is equal to ln of 3 over 5 over 3. Do not divide that 3 inside of this. This guy's stuck inside of it. It's not out in the open. Right? This is not a multiplication. Right? It's like a f of x kind of thing.
Log base 2.
Here we have a base 2. So I'd probably cancel that by doing log to the base 2 of both sides. So I plug in log base 2 of here, log base 2 of here. That would cancel. This gives me x squared plus 1 equals log to the base 2 of 5. This would mean that x squared is equal to log to the base 2 of 5 minus 1. And this would mean my x is equal to plus or minus the radical of log to the base 2 of 5 minus 1. It is possible for equations to have no solution, so we do have to convince ourselves that what's under the radical is positive. How do you know it's positive? Can you give me an approximate value for log to the base 2 of 5?
Like 2 point something.
2 point something. It's definitely bigger than 2, right? Because log to the base 2 of 4 is 2, and the log, we know the graph keeps going up. Right, so if this is log to the base 2 of x, when you're at 4, this guy is at 2. So when you're at 5, you will actually be slightly bigger than 2 somewhere. So here's a number that's slightly bigger than 2, you're subtracting 1. It's positive, so this radical makes sense, and so that's our solution. Right? If for some reason the inside here was negative, you'd say no solution. It can't work. So we'll stop there. We've covered everything we needed for the first test, which is on the 13th. So between this weekend and by mid next week, the latest, I'll post a review so you guys can focus on certain things. But make sure you do the homework for this, due on Tuesday, as well as we'll have a quiz on Tuesday on this material.
Just 1.6, right? That's your Tuesday. That's what we did today.
No. A quiz covers the entire previous week. So what we do today.
Yeah, but the homework, we only have 1.6.
Yeah, but the quiz on Tuesday will cover what we did today as well as Tuesday. So what we did on Tuesday is there.